we would like to get as much data as possible to figure out the nature of this object. It was shedding nickel with very little iron, for example, and the only place we find it is in industrial production of nickel alloys. So
Reports from the Minor Planets Center and NASA's Jet Propulsion Laboratory have just dropped, and they contain brand new data on the interstellar object 3I Atlas that is turning the scientific community upside down.
the trajectory designed by some intelligence. And of course, the best way to find out is to take a high-resolution image of it.
Collected right after the object's close pass by the Sun on October 29, 2025, the data at first glance looks like a routine update from two of the world's most trusted space agencies. But buried within those measurements lies a shocker. Evidence that 3I Atlas is behaving unlike any comet ever observed, as if it's propelled by something more than just sunlight and gravity. In the days following its perihelion passage, astronomers tracking the object noticed a sharp, almost explosive rise in brightness. Between October 31 and November 4, its visible magnitude increased by a factor of 5 in the green band of 0.464 microns, a level of brightening that stunned observers. For a natural comet, such behavior would typically indicate intense sublimation, as surface ice boils away under solar heating. But the sheer scale of the change in the short time in which it happened suggested that something more complex was unfolding. When researchers fed the latest astrometric data into dynamical models, they found that the trajectory of 3I Atlas could no longer be explained by gravity alone. The equations required an extra push, a non-gravitational acceleration. NASA's Jet Propulsion Laboratory reported a radial component of 1.1 times 10 to the minus 6 AU day squared, and a transverse component of 3.7 times 10 to the minus 7 AU day squared. Translated into ordinary terms, that means the object is being propelled by a faint but measurable thrust, as if something is continuously nudging it from behind. To understand what could cause this, astrophysicist Avi Loeb and his colleagues performed an energy balance analysis. The simplest explanation would be mass loss, jets of vaporized material venting from the surface and producing recoil, a rocket effect. Using a typical cometary exhaust velocity of around 300 meters per second, Loeb calculated that 3I Atlas would have to eject roughly 13% of its total mass to account for the observed acceleration. That's an enormous figure. For comparison, a regular comet losing that fraction of its mass would envelop itself in a bright, extended coma visible across millions of kilometers. Yet the space around 3I Atlas remained comparatively clear. There was no vast dust halo, no massive outflow to justify the thrust. This discrepancy led to two possibilities. Either the object truly lost that much mass in an incredibly efficient way, with matter expelled at velocities far higher than any natural comet could achieve, or the mechanism driving the acceleration was something entirely different. Loeb noted that if the gas were expelled not at 300 meters per second, but at tens of kilometers per second, the required mass loss would drop from 13% to just 0.01%, small enough to escape detection. The problem? Such speeds are not consistent with normal sublimation. They are, however, comparable to exhaust velocities of engineered propulsion systems. It was an unsettling thought, not a conclusion, but a scientific curiosity worth noting. Could an object behave as if driven by directed exhaust without being technological? Perhaps if solar heating triggered reactions that vented gas at unusually high speeds. Or perhaps if its surface material was metallic and unusually reflective, amplifying radiation pressure beyond what typical dust could achieve. Whatever the cause, 3I Atlas had broken the pattern once again. The strangeness didn't end there. The post-perihelion data also revealed a retrograde orbit almost perfectly aligned with the solar system's ecliptic plane. That detail might seem minor, but statistically it's extraordinary. the chance of a random interstellar object arriving with such alignment is vanishingly small. In Loeb's words, the orbit appears fine-tuned, a path threading precisely through the gravitational architecture of our solar system. Even more curious, the trajectory brings it close to Mars, Venus, and Jupiter, an improbable series of near encounters that seem less like coincidence and more like choreography. Then came the matter of composition. Spectroscopic measurements taken from ground-based observatories hinted at a chemical makeup unlike anything seen in ordinary comets. The ratio of nickel to iron in its emissions was exceptionally high, and its water content was startlingly low, roughly 4% of that found in typical cometary bodies. Such a combination implies formation in a region of extreme heat, where volatile materials like water would have boiled off early, leaving behind metals that could condense only under searing temperatures. It's the kind of environment you might find near a dying star or deep within a planetary interior, not in the icy outskirts of a system. Even its optical signature confounds expectations. Observers have reported extreme negative polarization, light scattered at angles that produce polarization opposite to what's normally seen in dusty or icy comets. The reflected light is also bluer than the sun, a rare trait that suggests the surface or ejected grains are unusually fine or metallic. Combined with the abrupt brightening, these properties paint a portrait of a body that's not merely reacting to solar heat, it's actively transforming under it. Perhaps the most dramatic observation came in the weeks following its close solar pass, when telescopes recorded a sunward-pointing jet and antitail streaming toward the sun rather than away from it. This phenomenon, while not unprecedented, is exceedingly rare and difficult to explain. It suggests that particles are being pushed forward, either by a peculiar combination of solar radiation and geometry, or by a directed outflow mechanism that we do not yet understand. For an object already showing anomalous acceleration, the coincidence is striking.
Loeb, ever the empiricist, doesn't leap to conclusions. Instead, he presents the possibilities quantitatively. If the observed thrust is due to gas outflow, then the mass fraction, speed, and thermal balance must align with the data, and right now they don't. If it's due to radiation pressure, then the object must have an extremely low density or an unusually reflective surface. Each explanation strains the limits of what we've seen in nature. The safest interpretation may be that 3I Atlas represents a new class of interstellar object, one whose composition or structure diverges sharply from anything native to our system. There's another subtle detail that adds to the intrigue: timing. The peak in brightness did not coincide precisely with the point of maximum solar heating. Instead, it came after perihelion, a delay that implies the outgassing, or whatever process drives the acceleration, responded not instantly, but over days. This lag could hint at thermal inertia within the object's surface, or it could reflect a mechanism triggered by sunlight-induced chemistry that takes time to develop. Either way, it departs from the behavior of standard comets, which usually reach peak activity before or right at perihelion. The data also reveal that 3I Atlas's orbital deviations are consistent over multiple observations, meaning the acceleration is not a one-off burst but a persistent force acting over time. That steadiness suggests an organized process rather than random jets flickering on and off. Whatever is pushing it, it's doing so smoothly and continuously, the cosmic equivalent of a steady engine burn. If this were a normal comet losing 13% of its mass, we would expect to detect a vast cloud of gas stretching across millions of kilometers, easily visible in wide-field telescopes. Yet when astronomers looked, that cloud wasn't there. The brightness increase was sharp but localized. The coma was compact. This mismatch between optical brightness and inferred mass loss remains one of the central puzzles. Loeb points out that the absence of such a cloud puts tight limits on the amount of ejecta, effectively ruling out the standard sublimation scenario unless the expelled material was ejected at extraordinarily high velocity. That leads to an even more provocative inference. If the acceleration is real and the mass loss minimal, the thrust per unit mass, what engineers call specific impulse, must be enormous, approaching values typical of high-efficiency propulsion. Again, that doesn't mean the object is artificial, but it does mean it behaves like something designed for motion. It's as if the cosmos itself built a natural analog of a spacecraft, powered by mechanisms we have yet to uncover.
It's this tension between data and interpretation that makes 3I Atlas so fascinating. Each new observation resolves one mystery, only to reveal another. The numbers are clear. It's the narrative behind them that remains elusive. Is this object an extreme outlier among natural bodies, or the first example of a physical process we've never seen before? For now, scientists are left with equations and uncertainties. A brightness surge by a factor of 5, a steady, unexplained acceleration, a retrograde, nearly planar orbit, metallic composition, low water content, bluer than solar reflectance, and a sunward jet. Each fact is measurable, verifiable, and real, yet together they form a pattern that feels almost deliberate. What's undeniable is that 3I Atlas has forced a shift in perspective. The assumptions that once defined what a comet should be are no longer sufficient. The data demand new models, or perhaps new imagination. In the quiet halls of observatories and the code of orbital simulators, researchers are now asking questions that a decade ago would have sounded like science fiction. What if not all interstellar visitors are passive relics of distant systems? What if some are, in a sense, active? Until more observations arrived, the truth remains suspended between hypotheses. But one thing is certain, 3I Atlas is not ordinary. Its behavior challenges the limits of what natural physics has shown us so far. Whether the explanation turns out to be exotic chemistry, unknown material properties, or something far stranger, the object has already achieved something remarkable. It has reminded humanity that the universe is still full of surprises. As the data continues to pour in and the object drifts back into the black, astronomers around the world are left watching, calculating, and wondering. Somewhere out there, beyond the orbit of Jupiter now, 3I Atlas keeps moving, silently, steadily, and against all expectations. Whatever force drives it, one thing is certain: it has already changed the way we look at the skies.